Now be careful. So the first derivative test. You take the derivative, you set it equal to 0 or undefined. You determine whether the derivative changes signs at that critical number. If it does, we've found a relative extreme value. So we changed that process from first derivative to second derivative to find points of inflection. So people are going to think, oh, that must be what the second derivative test is. But no! It's the same process, but we're finding a different thing, right? We're finding points of inflection with the second derivative than the first derivative. So when we talk about the second derivative test, we're actually not talking about finding points of inflection. We're still going back to that same question of how do we find relative extrema. Okay? This time we're going to be using the second derivative instead of the first derivative. So I think that pictures are going to work the best here, because people tend to forget otherwise. But if we just draw a picture, it's going to be completely obvious. We're going to start off with one scenario. If we have a first derivative equal to 0 at a particular point, and the curve happens to be concave up at that same point, well, if we draw concave up, and we find the point where f prime of c equals 0, that would be this point right here, then it's obvious that that point, c comma f of c, is a relative minimum. Just draw a picture and you'll see it. And if the first derivative is equal to 0 and the second derivative is negative, or if we're concave down, draw the frown, we find the point on that concave down curve where the first derivative is equal to 0, then it's completely obvious that we're looking at a relative maximum. So that's what the second derivative test tells us. We're still finding relative extrema, but we're using the second derivative instead of the first. Finally, if we have the second derivative is also equal to 0, that's, as we saw before, that means nothing. We could have a relative maximum, we could have a relative minimum, we could have neither. It just depends on the function. So that's the second derivative test. It's pretty easy to use, and we like it when we get into Taylor polynomials, which is towards the end of the class. So keep that in mind. So here's a quick example. F of 3 equals 12, f prime of 3 equals 0, f double prime of 3 equals 1/4. Well, the requirement here is that the first derivative equals 0. So if the first derivative equals 0 and the second derivative is positive, then we must have a relative minimum. What is that minimum? Well, the relative minimum, f has a relative minimum of 12 at x equals 3 because of the second derivative test. End of story.